Okay, so should we start? Yep. Okay, great. So units. So I guess as everybody learns in their first year algebra class, algebras are supposed to have units for all sorts of reasons. And so factorization algebras don't come with units. What is a unital? Factorization algebra. Well, you can try different. So first of all, if you think about this picture, and things colliding, you realize that this picture is only like there's two structures to an algebra. One is multiplication, and the other is what is the unit element. So this kind of picture of points colliding, this really only encodes the multiplication. There's no room for unit. So version 0. So naively, maybe the way that you would define a unital algebra, you would try to define a unital algebra is, first of all, there is a unit algebra. Namely, the dualizing complex of the Ron space itself. That's a perfectly good factorization algebra. It's canonically a factorization algebra, and can ask. Kind of a map of factorization algebra. But of course, yeah, even in the world of ordinary algebras, this is not what a unit is. So a unit is more. It's more in all sorts of ways. For instance, if we're talking about associative algebras, this needs to be central. It has to satisfy a whole bunch of properties. And in general, this kind of approach, one can bootstrap from this kind of approach to the correct notion. But that's not the. But I want to describe a more geometric approach that comes with some cost, unfortunately. So the rough idea is that for every point, we want to have a map from just like the one-dimensional vector space to the fiber at that point, which will name the unit there, and that somehow that's compatible with factorization. Oh, what I mean by this is, for instance, there should be a map. If you pick 2 points, there should be a map from the thing corresponding to 1 point to the thing corresponding to 2 points, because by factorization, this is just the tensor product, and you can apply the unit on one of the factors. It's this kind of structure that we're after, kind of coherently so. So the point of writing this is, hopefully this is suggestive that this has to do with inclusion of subsets. And so, like the Ron space parameterized subsets, and so the idea of this kind of formalization of units is to remember that subsets have more structure than just a set. There's an inclusion relation. Yeah. Just to remember the inclusion relation. And subsets. So unfortunately, we have to grapple, though, with the following issue. So we can do that, but we have to grapple with the following issues, that these maps that we want to specify are not isomorphisms. They're necessarily not. I mean, if they were isomorphisms, then this would just say that our factorization algebra was itself the unit. And so, if we just sort of included something like this, here then, if we try to build a pre-stack that does this, it would automatically force these maps to be isomorphisms. So what we have to do is kind of step outside this world of pre-stacks and consider something more general. We need to consider categorical pre-stacks. So AKA pre-stacks valued in categories. So before, all our pre-stacks were valued in groupoids. So now, just as well, we can consider, so in other words, functors from the opposite of affine schemes, now not to groupoids, but to categories, maybe. So let me just name the main example that we'll want to consider is the Unital run space. Name an example. Unital run space. This is, well, it's just a poset, which I regard as a category of finite subsets. Well, same thing. Maybe let me just verbally give a brief warning, is that there's some disagreement about what exactly this space should be called, namely whether it should include the empty set or not. So for the purposes of this, in the end, it doesn't much matter. But for the purposes of this talk, I want to include the empties. So that kind of makes things some things a little bit nicer. So this is just category, by inclusion of all possible finite subsets. Okay, so this is this is the object that's going to govern unital factorization structures in the same way that the run space govern ordinary factorization structures. And so some facts. Well, let me say some things about kind of this general formalism of categorical pre-stacks. So something that's not surprising if X is the categorical pre-stack, we'll consider all our favorite kinds of sheaves. Without any difficulty. So abstractly, what you can say is that each of these symbols by themselves, varying the variable, is an example of a categorical pre-stack. It's something that takes affine schemes to categories, namely those ones, and this is just kind of a mapping category. That's an abstract way to say it. But let me spell it out a little bit more concretely. I don't know which example. I don't know. Let's say F. Let's say a quasi-coherent sheaf is the data of so first of all, for every S point in X, X, quasi-coherent sheaf on the thing. And now the new thing is that there could be maps between S points. So the S points now form a category rather than a groupoid. So I can have an alpha from X to X prime. So that's, and I'm supposed to, and well, not surprisingly, I'm supposed to get a map of quasi-coherent sheaves. And then compatibility. With composition. Let me not spell that out, other than to say, in the usual world of pre-stacks, this would be one thing, is that if you have map from S to S prime, then the resulting thing, if you take a composite point, that's pulled back. So in this more categorical world, there's an extra condition. There's two kinds of compositions. You can compose one morphism like this, or you can also compose a one morphism with a two morphism. So like if you have two S points and a map between them, and you have S prime mapping to S, there's a commutative diagram that you can write with these things. Anyway, I'll leave it. I'll leave it as an exercise to work out, and dot. It's this kind of structure. Okay. Shouldn't erase that. So now let me give the definition, and then I'll try to unpack it. The definition of a unital factorization algebra is the same as that of a factorization algebra, except replace Ron by Run unital. Unital factorization algebra is data of
with the concerning composition, if it X to expand with double prime, do morphisms compose?
Yes.
Or there is okay.
Yes, morphisms compose strictly, yeah. I mean, there's no room.
Yeah, no.
I mean, if there's something, then they have to compose strictly. Yes, they're not unrelated. So it's a view module on Run unital, and also factorization, which. So maybe I guess I should say, but tautologically, on these categories, they're pullback functors along maps, exactly because this is maps because of how it's defined. Oh, I'm just writing exactly the same thing, but with unital. So that's the nice thing about this formalism is I get to make exactly the same definition, and it builds in, I claim, exactly what we want. But so let's unravel. Let's unpack that.
Don't we need to impose the fiber that instead is escaped?
We need to impose that. Yes, we do. Indeed.
Before this union for shriek.
What's that? Oh, upper shriek. Yeah. Sorry, it's this. It's already a Durham stack, anyway. But yes, that's what it should be. So D modules come tautologically with a Schrick restriction sum. Yeah. I mean, I guess maybe asking for having to ask for this thing is one downside of including. Okay. Oh, well, so here are some example points. So consider some K-forms of the Unital round space. So K points is just, well, it's the, so what are we supposed to get? So for any finite subset, we're supposed to get A sub x. So this is just there's just a tensor product of the corresponding points.
No, let not be. S is not very good.
S is not.
This
Oh
was a
yes,
scheme.
thank you. What's that?
It was a scheme.
Oh yes, S was a scheme before.
Capital I.
I.
J. J is fine.
Sure. I don't like I because I before was an abstract finite set. But anyway, so this is a just some vector space. So this is supposed to be the tensor product over all the elements of the singleton. This is what factorization does. And now if J is included in J prime, then I'm supposed to get a map from AJ into AJ prime. Let's consider. So for instance, J could be the empty set, and J prime could be a singleton. And so this gives a map from K, which is the value on the empty set, to the fiber at any point. And similarly, if like similarly, all of these, and so this exactly encodes coherently what all of these kinds of all of these kinds of things. And so we have the notion of anyway, I think for the moment this is all I wanted to say about what a Unital factorization algebra is. So the next thing that we can say is just like for non-Unital factorization algebras, we have the notion of factorization homology.
Oh, could you explain the how this map from AD to AD prime follows from this definition? How is it
Because this is a map in the category of k-valued points of this. So the k-valued points, this is now a category. This is the category of finite subsets, and there's a map from one to the other if there's a unique map if there's an inclusion. And so if you have an inclusion, like I said, if you have a sheaf, if you have a map between S points, then you get a map between the corresponding sheaves. So these subsets I think of as just K points, so sheaves on spec K are just K complexes, or we're calling vector spaces, and so you get a corresponding map just from the formulas.
Here with multiplicativity, do you need to impose kind of naturality, or is it automatic?
Naturality.
I mean that if you like
There are 3 dots here. That if you
Yeah.
have like 3 copies,
yeah,
is that what you mean? Yes.
that I mean the inclusion of the unit, for example, should be like the two dots to 3 dots should be a empty including into one, right?
So this will follow from all of these.
Okay,
Yeah.
by just knowing.
I mean, because this is taking place on the unit. This is an isomorphism on the Unital. run space.
Okay.
So just from that will also encode all of the naturality of the sort. I mean, of course, I did this for 2 copies.
Yeah.
The dot means you do this for arbitrarily many finite with many copies of this. All right. Optimization homology.
Wait a minute, I have 2 deep questions. The first is like, given a unital factorization algebra, how do I say this language pass into the underlying unital factorization?
Yeah, I'm about to.
Great.
I'm about to do that.
Great. And the other one was units should have the property that when I multiply by them, nothing happens. How do I? How do I?
Well, I don't. Let me not answer that. The reason I declined to answer this is because we've taken the approach that we decline to answer what multiplication means. So I don't know how to answer that without having a discussion about what multiplication is. In what sense is a factorization algebra an algebra? But yes, that's an excellent point. Had we had the discussion, then it would be the case that acting by unit that does nothing in the way that you expect. All right. So the point is that, well, we have a natural inclusion now. So, I should say, first of all, so this unital run space. Let me just unital can also be expressed in terms of powers of x over finite substance. Let me not say exactly how. So namely, you have, well, first of all, you replace in this definition that I erased, you don't ask for surjections, you ask for arbitrary maps, and then rather than taking the colimit, you take what's called the last colimit, but it's not quite that, you have to localize that so that surjections, these are, but anyway, that's not the point. The point is, it's a colimit of some diagram involving terms that look like this. And the point of that is that each of those terms is proper. And the consequence of that is that this canonical functor just like in the non-unital case, has a left adjoint. Probably should have given it a name, but oh, okay. Let me regret it in a second. So it has a left adjoint, and so we can define definition. A is a unital factorization algebra. And the factorization homologies, and they kind of rewrite the same definition. This is by definition, this left adjoint applied to the underlying D module on the unital runs. But now you can reasonably ask the question of what is this and how can we calculate this and what's the relationship? And now let me address Verbier's question. So this is just formally parallel. And now the point is, here is kind of part of the magic of the run space. So there's a natural map on the run space with T to the unital run space. So it's like the underlying groupoid, and you throw out the empty set. Yeah, on S points. Well, like what is a? I mean, any ordinary pre-stack you can regard as a categorical pre-stack. Just the category happens to be a groupoid. It's strictly a generalization, and in that world, there's a map like this. So on S points, so an S point of this is a finite non-empty subset of X of S reduced, which in particular gives an object in the S points here. So there's a natural map, and let me state that it's a theorem, which is a concept. The corollary is that if I can first restrict. So actually, sorry. So restriction along this preserves having the structure of factorization. So this gives a functor from Unital factorization algebras to just factorization algebras. So this is the answer to Gerbier's question. And also a corollary of contractibility of the Roland space is the following remarkable fact, that for any D module whatsoever in the Unital Roland space, this has nothing to do with factorization. This is just kind of the internal structure of the space. We can do the following thing. We can restrict it. And then we can take and then we can apply this left adjoint on the non-Unital Roland space, on the ordinary Roland space. And this is the same as just doing this on the Unital Roland space.
Different pi.
Different pi, yeah, maybe pi Unital. Yeah, is that better? Yeah, so this is so in fact, this definition of factorization homology that I gave, if you have a Unital algebra and you forget it to a non-Unital one, it doesn't change the answer. It doesn't care about it. Okay. Bit behind schedule. Well, any questions about this stuff so far? Okay, so one. Okay, so what's the advantage of having units? What does it buy us? Well, buys us the following thing. Actually, maybe for the purposes of time, let me move on for the moment to a kind of a slightly categorified setting. I want to make sure that we have everything we need for the next talk. So, glorified version. We can have Unital factorization categories. So just like we have factorization algebras, we can consider sheaves of categories on. So yeah, the way we're going at categorical level up is the kind of sheaves matter. So it's sheaves of categories. So I think I'm not even going to write. This has the obvious definition. This is a sheaf of categories on the Unital run space with factorization. But I want to find in an evident way. But now I want to kind of describe a more concrete way of thinking. More concretely. It's the following thing. Oh, so Y is a categorical pre-stack. We can think of any kind of sheaves on Y as follows. So if you're not anyway, so if you don't like this notion of categorical free stacks, here's a kind of a much more down to earth way of thinking about it. There's a simplicial object. This is the stack of objects. Free stack. So now it's an ordinary free stack. So this is here. So in general, the way it's defined is, well, you evaluate Y and S. This is some category, and you can take the maximal subgroupoid. And then this thing has a groupoid acting on it, which is a stack of morphisms. So explicitly, the notation is key, and so on, but I'm not going to write down. So kind of explicitly, what is an S point of this? The notation maybe is a little bit funny, but this is the same thing as like 2 points in Y of S and a map between them. So you can have a pre-stack that parameterizes pairs together with a map. So in this kind of categorical world, there's different ways of taking this is playing the role of some kind of a product. That's so a product would be just 2 points. This is 2 points with a map between them. And a sheaf on Y is the data of a sheaf F on this underlying groupoid with the following thing. You pull back along the source and you pull back along the target. I hope it's clear. There's a S projects to T to X here, T projects to Y, and you specify a map between them, plus some compatibilities, which I'm going to ignore. So this is kind of a down-to-earth way of thinking about what any kind of sheaves are. So I guess now we'll apply it to sheaves of categories. The same kind of formalism holds. So that it's so this underlying groupoid. Well, it's essentially. Now I'm going to cheat a little bit and ignore the difference between run space and an empty point. This will be just a sheaf on the run space. This. So let's apply to our situation.
So is this diagram like a last column to Y? Something like
this. Yeah, so there's a precise sense in which Y is out of this diagram, you can build a colimit diagram for Y. Let me not say exactly how. If the words are familiar, the keywords are Gauss-Field con. Okay, so apply this to.
Maybe just completely the answer is S and T play an asymmetric role here, so it's not just some purely categorical thing about this diagram.
Sure.
Which the basket kind of thing saying.
Yeah.
Can't just be.
Yeah, it's not just the colimit of this diagram. Indeed, it's a colimit of something standard built out of this diagram. So let's apply this to this unital round space. So the underlying group point. This is just the usual round space. Well, disjoint union and an extra point, which I will ignore. I'll just pretend that this is that it's this. And now what is this guy? This guy parameter, let's say what S points are. The S points are two subsets of the are 2 points on the round space together with an inclusion relation like this. This is what. So let's give this a more suggestive name. Round sub inclusion. So this is the pre-stack that's parameterizing these kinds of things. And so let me just rename things in this diagram specific to this situation. We have this round sub inclusion mapping to the round space in 2 different ways. And we'll call it P small and P big. Suggestively, so this picks out the smaller or the larger subset. This is what corresponds to the source. This is what corresponds to the target in that general diagram. So the upshot. Let me name the upshot is that if C is a so notice in this description, Y groupoid maps to Y, and the sheaf that you're supposed to associate on Y groupoid is the restriction. So suppose C is a factorization category. The data of unitality on C is given by. So explicitly, if you have a factorization category and you want to upgrade it to a Unital factorization algebra, well, you have to give this kind of equivariance with respect to this thing. So you're supposed to say, well, C is a sheaf of categories on the round space, so you're supposed to pull it back on the small projection, and you're supposed to map it the big one, and maybe compatible with dot dot dot. So it's the essential piece of data. And now what's that?
Why here offers stop?
Oh, I think is that not? Do we have a notation for pullback of sheaves of sheaves of categories? All right, has that come up yet? Should I change it? What's that? Well, no, but this is sheaves of that was for D modules.
Also crystal.
I know. I know.
Ecologically, people write buffer streets for the demodule fallback for good reasons that are related to like pre-module.
Yeah. Here it's
It is quasi code of Extron, and then you would call it upper star, but like actually people who think about sheets who kind of get offended by calling that upper star, they call it upper street. But when you're in the world of sheets with categories, it's like fair game to do whatever you want. So then upper star, not at all. That's
yeah. Anyway. That's the notation. Anyway, there being no good reason to change the notation, let me stick to the notation in the paper. Which is this one. And so I don't know. Let's say a fact is that
But I have so why are you giving this discussion now for the categorical thing and you didn't say it earlier for the?
I could have said it. I mean, this it's a categorical version of this discussion. Is what is happening. Yeah, maybe that's the. I could have said the same thing, but then it has a kind of an easy unraveling. There's something about categories that I want to use this for that I didn't need it for in the. Indeed, the very same discussion would have been fine. That's setting. Oh, okay. So this pullback. Oh, whoops, small. It has a right adjoint.
You're not right under the chat.
Oh, is that better? Yeah. It has a right adjoint called a small lower star. So this has nothing to do with this map in particular. It has everything to do with the fact that there's some properties to the situation. It's because oh, did we use this word? So these are ordinary pre-steps. Did we use this word pseudo proper? Has that come up? Okay, never mind. So the run space has some properties to it, and for this reason, you have some extra adjoints. And so the point is, I can rewrite this as rewrite the structure as a map, part of the structure from like C to this. Let's see. So more explicitly, we'll do this. So suppose I'm going to suppress S from the notation. So suppose I have kind of an inclusion of two generalized points. So this is, I think of this as an S point. I guess either way, either as an S point on this, or as an or as a morphism in the unital run space. And so what I get is a functor called ins that ins unit, sorry. Inside X prime goes from the category associated to X to the category associated to X prime. So this is the kind of structure that I get out of this. And okay, so let me do an example so that we know what we're talking about. Perhaps an example. So unfortunately, I think this has not come up. So what's that? Oh, Oh, yeah, so one is KL, we did, that example did come up. Thank you. A second example I wanted is that A is a factorization algebra. There is a a weak factorization category of factorization modules. So Kevin in his talk defined what these are for particular points, and it makes just as much sense for generalized points. And the assertion is that these fit into, more or less obviously, this fits into a crystal of categories over the run space. And in fact, if A is a unital factorization algebra, same thing over the unital.
Concern. So
Yeah,
this is all.
I mean, I think I'm getting to what you want me to get to.
Yeah.
In a few minutes. I'm trying to short circuit to there.
Okay.
I have a destination in mind.
Yeah, but we need to reach that.
We do, yeah. So all I wanted to say is that in this case, its unit from like let's say empty set inside one point. This just puts in the vacuum. So one of the examples of a factorization module that came up in Kevin's talk is the algebra itself acting by itself. And what this ins unit does in that case is it takes the unit to this module, which is the, so like if you think about this as somehow analogous to bimodules has a tensor structure where the algebra itself is the unit. So this is playing that role. Okay, so that's for the moment what I wanted to say about this example. And now I want to, just very quickly abstract from this discussion of factorization algebras and factorization homology to kind of a slightly more general setting of kind of general local to global functors. So before that, maybe so now let's see, let's take a look. We will Unital. Well, actually, let me just use the structure. The crystal categories. Categories. The unital round space. AKA. So that's like usually it will have some factorization structure, but this is not relevant. And C below category. As per convention. Non-unital. Unital. Local to global functor. Is a map from this local people categories to, well, we just take a constant D modules in the unital round space. I tensor this with C local. So it's just it's what you think it is. It's guess by adjunction, it's the same thing as just functors from some kind of global sections of this into this category. I want to think of it like this. And so note is what happens with units. So what happens with units is the whole kind of thing that. We have this,
Sorry, what is it? Was it fine to be unit though?
no, this is, sorry, this is a,
It's a
this is an
unit.
atomic, this is an atomic term, unital local to global.
Yes, but.
Because it's taking place on the unit
Something about this functor.
No, it's not an adjective describing functor. The word is unital local to global functor. It's a bit of a mouthful, admittedly. What?
He's giving a definition.
Yeah, that's the definition. Maybe like this. Is how it should be pronounced. So, well, what happens with units is the following kind of thing. So we have this, well, just like before, we have this ins unit. Works on x and sine x prime. So this maps with C local x with C local x prime. And so how is it? Oh, let me call this f. If I have a name. And so how does this f work with regards to this? Well, what happens is that we have an isomorphism, so the unital structure. Or maybe like a word about terminology. So non-unital would be the same thing, but restrict taking place over the regular ones. So by unital structure, I mean the thing that upgrades from a map on the regular round space to the unital one. So roughly, it's the following data: is well, there's a functor associated to the point x1. X, and there's a functor associated to the point x prime, and I'm supposed to and I'm supposed to give an isomorphism like this. This is what that amounts to.
Nick,
Diagram.
What's that?
yeah, it's just a punitive triangle on top.
Diagram. Reach that.
The commutative dot. Oh,
Just
And then take the
diagram.
arrow,
sorry. What do you?
take the arrow on top and underneath, right, C globe. Nope. Up.
Oh.
Top. Nope, keep going up, Amazing, now like C globe there.
Yes, it's this. Yes. This. Let me rewrite what the commutative diagram is saying. Indeed, it's just so the unital structure is exactly compatibility with this. And well, in particular, I want to think of it as a map, as an isomorphism like this. I deliberately drew the arrow in this direction so we can weaken this. To a lax unital structure. Star, where star need not be an isomorphism.
So is that truncated diagram just coming from definition?
Yes, this is coming from the definition unraveling of such a functor X. Oh, because its unit on this guy doesn't do it. This is the constant chief. But it's the its unit, so for every point, the section is like C below, and its unit is the identity. I mean, I could have put in a corresponding its unit. That's the reason not to do it. Okay, great. And so we have the inclusion of categories. functors local to global Unital from okay, I hope it's clear what this notation means. It's the category of all such functors. And this of course includes into the ones that are lax unital. And what is maybe a surprising fact is that this functor, I hope it's clear, it's just suppose we didn't require this condition. And the claim star star is that star star has a left adjoint. So there's a way of taking a kind of a lax unital functor and turning it into a kind of a strictly unital one. And given by, we'll write the formula. So if I have a functor f, this goes to the following thing. And so the last thing I'll do is I'll write down the formula for it, and then I'll unravel it in the example. In the example of factorization modules over a factorization algebra, just to recover something familiar. Oh, so it looks like this. So this f ins unit integrated ins unit. So what is this? The following thing is, well, let me write it on. Let me write it on the z points. We're on space. So you take the local category, do insertion of unit. I'll explain what this notation means in a second. To this you can apply the functor f to get the modules of this guy, which I have to explain. And then I integrate this out to insert the modules on z. So the kind of thing it's supposed to be is it's supposed to start with the category associated to z and end up with this global category associated to z, which is this one. So where this guy is just the fiber product. B with a run space. With a run space. Where this inclusion is the big projection. So in other words, it's like you're looking at this is like all points of the run space that contain the given z point that you chose. That's what this is. That's what this is, and so this ins unit. This is the natural target of ins unit, which is what's this projection? What's that? That projection was. No, this maps to run. You want things that are bigger, yeah?
Yes.
Yeah. So sorry, small. Yes, sorry. Small. Yes, the small part agrees with the z point. Yes, great, thank you.
That's a definition, right?
This is the definition, yes. Okay, so the assertion is that this funny composite, which sort of inserts the unit and integrates this out. So this part is inserting the unit, and this part is integrating it out. is what this is. So in the remaining I think I'm exactly out of time now because I started 5 minutes late, but but I'll take another minute to unravel what this means in a particular example.
So while you're writing in particular, if I started with an actual unital thing, the fact that I get it back is unital.
What's that?
If I actually started with a genuinely unital,
The fact that you get back what you started with is not completely obvious.
But it's related to contractibility. right?
It is of course related to contractibility of neurons. So I wanted to do it in the example where it would be kind of more clear.
Also, it's containing the fact that this actually provides a left.
Yeah, so the inclusion is fully faithful. So if you include something and you fully faithfully and you apply any kind of adjoint, you get back to where you started. It's implicit in the assertion. So this is supposed to generalize the following example. That's a key example. Is where is factorization A modules for a factorization algebra A or a unital. Factorization algebra A and F is a functor is a like a local to global functor to vec, which forgets F of M is the underlying module of F. I think this was defined in Kevin's talk. Yes, is that correct? So like the data of a factorization module comes with it's like this is just evaluate on the point of the run space on which M lives. That's the kind of the underlying vector space. And so I don't know, let me say it as a claim is that if I do this integrated insertion of unit, this produces the functor of factorization homology. Which I realize now I did not define in the case of modules, but it's defined easily enough, which is you forget down to as before, you forget down to a D module on the run space, and you integrate that out.
Pointed run space.
What's that?
Well, pointed run.
Pointed run space, yes. So the factorization module was defined to be in particular a D module in some pointed version of the run space. So you can just forget about all other structure, and take the take homology. It's left adjoint homology with compact support.
These forget it font for you for anyone that can order it for the data model or
What's that?
power model. Like when you forget, like if I have model supported.
If you have a module supported at a point, that's an object of this category, the fiber of this category at a point. So this is supposed to map to the fiber of this category, which is just vec, which is the underlying mod. For a more general kind of point, this is supposed to produce a sheaf on the parameter space.
But your functor is supposed to produce local to global functor.
Yes, so-
not just an object.
What's that? So here is a local to global. This I claim. This is a this is a lax unital. This I just named a lax unital.
Sorry, back to C globe, right? So it really stands for kind of DMOD underlying long interval there.
Yes, so
It means okay, awesome.
yeah. So take C globe to be vec. So this defines this forgetful functor defines a lax unital local to global functor.
But the answer for F integral is supposed to be unital over the global frontex, right?
Yes.
But what is in the right hand side, it doesn't seem to be.
Oh. Yeah, maybe let me explicate this a little bit. Which is or if you have a z point of the Ron space, what is it that you do? So f ins integral ins unit sub z of some module m. So the claim is that this is pi lower 3 of m
The inclusion.
z inclusion. Yes, thank you.
Over.
So this is a d module of z.
Yeah, it's I small,
Pi small. Oh, p small. Yes.
but it's P small, yes.
Lower 3 p small. Amount from z. So when it's so the fiber. Notice that the fiber at this point is exactly the pointed Ron space containing the corresponding f of z.
Maybe you want to say that this M subscript C contained is exactly the structure.
Yeah. So this
This is what this is.
so this is the pullback to this guy of the module over of the module as defined as a d module on this pointed Ron
It's
space.
exactly the T module on the Ron space, the code structure.
Yeah.
Which module that will be on space.
Yeah, that's right. So I mean, in particular, if z was a point, then this thing is exactly the pointed Ron space. So in Kevin's talk, a factorization module was defined as in particular a d module in that. For more general parameters, a factorization module is defined as a d module, and this guy together with some structure, but we forget that, and for the purposes that extra structure is not relevant for our purposes here, and in particular we get this expression. So this is what I've been calling. Since z was a point, this would be really factorization homology with coefficient in that module at that point.
So the plane is completely tautological.
The plane is tautological now.
And let me just say one more time. So like this procedure explains where factorization homology came from in some sense. So like it's obtained by this general factorial procedure of applying radical geometry. And so get from factorization modules. The vector spaces and this the unit in A makes this functor relaxing so that it's not unital. And you want to make a unital in some universal way. This is the way you obtain this from the factorization.
Yeah.
Can I just add one brief word here?
Yeah.
So there's two functions. Okay, if you have a factorization module, maybe setting at some point, say it's M, it has an underlying vector space. Now, if you take another point, you might have like N sitting at that other point. There's also a vector space. So the underlying vector space here is the tensor product of the two.
Yeah, that's right.
And if N happens to be the vacuum, you get very different representation, very different vector spaces. What this all is saying is that chiral homology is adjusted so that it receives a map from the forgetful functor. So M maps to its chiral homology with the basic property that if you add the vacuum at another point and then take chiral homology of the result, you get the same answer. So that's what all this is saying. It's think of it as a correction, although why it corrects maybe that doesn't. I mean, but what is a correction to exactly might not be a priori meaningful to you. But what it's saying, what all this is saying is you take M, take its chiral homology, that's the same as chiral homology of M, but like answer and take the vacuum.
Sorry, let me write down what you said. I wanted to say that anyway. So thank you. So suppose you just have a module sitting at a point. in the way that really was defined in Navier. So the fact that we have a natural transformation like this means in this case that that there's a map of vector spaces from this to the factorization homology. Factorization homology. To this guy. That's what the unit of the adjunction is doing. So this is what you might call correlators. So like this to like a point in M, you get a point in factorization homology. But indeed, if you have M and N, M sitting at the point X and N sitting at the point Y, what you get is similarly a map like this. And in particular, if NY is just A, then you can just forget it. And if putting in the vacuum representation, putting in this unit representation at some point doesn't change what the factorization homology is. This is part of what it means for this thing to be a unital function. Anyway, this is what Sam was saying, and indeed this is the key. This is one of the key features of vector. I mean, in some sense, in the sense that of that assertion, factorization homology is kind of the best approximation to the forgetful functor that has these properties.
We'll see a bunch of examples in next talk.
Yeah.
Exactly this kind of phenomenon that you start with the function, which is like unital, and then you make this procedure and the result without the unital something very small because something you want to be as strong.
Can I just quickly ask something about the notion of the unital local to global functor?
Yes.
Namely, do we assume this to be like, or require this to be d mod Ron unital linear somehow?
Yes, that's what it means. Sorry, these underlined means that this is a map of crystals of categories. This is a map of sheaves
so
of
this
categories.
is all happening like linearly over d mod.
Yeah,
Fine.
that's right.
Okay.
So let's technique and then I have a procedural question.
Yeah.